Let's look at some examples of how to work with the first fundamental theorem of calculus. Remember that this theorem guides us in how to evaluate a definite integral by using antiderivatives. In this first example, we are going to evaluate the integral from 1 to 3 of 2x squared minus 3 dx. Remember, the first step is to take our antiderivative. In this case, that would be 2/3 x cubed minus 3x, and we're going to evaluate that from 1 to 3. Remember that according to the first fundamental theorem of calculus, we substitute in the upper limit of integration first. So we would have 2/3 times 27 minus 9. That's what we get from substituting in the 3. Minus, now we need to substitute in the 1. And we would have 2/3 minus 3. Simplifying that, we can cross-cancel some of this. So we have 18 minus 9, that's going to be 9, minus 2/3 minus 3. If we think of our common denominators, this would be 2/3 minus 9/3, which is going to be a negative 7/3. And if we add these two together, once again thinking of our common denominators, we'd have 27/3 plus 7/3. That gives us 34/3. The great thing about these is we have a very simple way that we can check these on our graphing calculator. So let's go ahead and try that. If you go to your quit screen, we're going to do Math 9. You'll notice it's function integral, and assuming you have the updated operating system, your screen should look something like this. And all we're going to do is simply type in exactly as we were given the problem. Instead of putting the integrand under y1, I'm simply going to type it in right here. Notice it looks exactly as we were presented with the problem. We get as our answer 11.3, but remember we had done fractions, so let's go ahead and double check to make sure ours is the same. And it is. As you're doing these on your own, definitely make use of the fact that you can very easily check all these on your calculator. Let's go try a few more. Here we're going to evaluate the integral from 1 to 4 of 3 square root of x dx. We could rewrite this problem if you wish as the integral from 1 to 4 of 3x to the 1/2, if you find that helpful. The 3 I can bring out in the front, and now I'm going to just do the antiderivative of x to the 1/2, which is going to be 2/3 x to the 3/2, evaluating that from 1 to 4. Because of our properties of integrals, I could go ahead and cancel these 3's right away. That might make my arithmetic a little bit easier. We substitute in the 4 as the upper limit first. As we take 4 raised to the 3/2, remember that's going to be square root of 4, which is 2. 2 cubed is 8, times 2 is 16. This will be a great example of a problem you could see on the non-calculator multiple choice. Notice all that nice arithmetic you just had to do in your head? They love to give you problems like that. Minus, now we're going to substitute in 1, and that simply gives us 2. So our answer is 14. We could go ahead and double check that one on our calculator really quick. Remember, it's Math 9 for function integral, and we're doing the integral from 1 to 4 of 3 square root of x. If we were to graph this, remember the interpretation of being the area under a curve. So if we were to graph 3 times the square root of x, and we were to use our second calc feature and do number 7 for our integral, remember that other interpretation of this is really that of being the area under the curve between 1 and 4. And this gives you a really nice visualization of that. In our third example, we now have a trig problem. We're going to evaluate the integral from 0 to pi over 4 of secant squared of x dx. Doing the antiderivative, remember that antiderivative of secant squared of x is tangent of x, and we're going to evaluate that from 0 to pi over 4. Unit circle time. Tangent of pi over 4 simply is 1. minus tangent of 0 is 0, and we get 1 as our answer. Another type of problem they like to give you on the AP exam because it requires you to make use of your unit circle knowledge. Now we're going to look at an exponential function evaluating the integral from 2 to 5 of 3e to the x dx. Taking the antiderivative of e to the x is simply e to the x. We substitute in 5 first as the upper limit of integration, minus substituting in the 2 as the lower limit. You could easily leave that as your answer. If you want, you could factor out the 3 as the greatest common factor. You could even obtain a decimal answer, an approximation if you want. The approximation is pretty large. It's 423.072. Were this a non-calculator part of the AP exam, of course they would leave the answer in exact terms in terms of E. The last example we're going to look at draws upon that interpretation of a definite integral as the area under a curve. And in this problem, we're asked to find the area of the region bounded by the graph of y equals 1 over x, the x-axis, and the vertical lines 1 and e. You could graph it on your graphing calculator if you'd like. I'm going to just draw a picture of it here. The graph of 1 over x, of course, is asymptotic to the positive y-axis as well as to the positive x-axis. And we want the region between the vertical lines x equals 1 and x equals e. So you see in yellow the region of which we are finding the area. To get the area, we're going to set this up as the integral from 1 to e of 1 over x dx. Evaluating the integral, according to the first fundamental theorem of calculus, we know the antiderivative of 1 over x is natural log absolute value of x, and we're going to evaluate that from 1 to e. Substituting the upper limit of integration first, we'd have natural log of e. Now I can lose the absolute value bars because e, of course, is a positive value anyway, so the absolute value bars don't really mean anything, minus natural log of 1. But natural log of 1 is 0. Natural log of e simply is 1. If you think about it, it's kind of a neat answer. This is saying that the area of this region is a perfect 1.